Yeah. So so here is a list of activities. So one activity is writing this textbook, which I'm doing together with professors from Purdue and the publisher. So I think name of the publisher is Cornelia, and this book is to like introduction to like everything, and particular chapters I'm involved like is about logic designs and CPU, and the like our claim to fame is, first of all, we are using examples which are not vendor specific, which are not like FPGA vendor specific. So when professors do FPGA labs in school, they usually just use some set of the boards which are like either from Xilinx or Altera or somebody else, and some professors spend like 20 years with the same board because all their classes and labs are connected to this board. And what I found is that if we make seminars to like a large number of people, like to like 25 universities at the same time, doing some labs, it's not practical for whoever sponsors this activity to buy like hundreds of boards, because this is like large spending, plus those boards are going to become obsolete and they need to be updated. But usually every school has some boards somewhere, and it's better to make examples which are kind of isolated from the board. And this is actually what we did. So we created wrappers for like more than 40 different boards from like Xilinx, Altera, and so on. So this is like one like a claim to fame. A second claim to fame is that most of introductory logic design classes are sort of boring because they were created using a recommendation of IEEE and like me, and it has stuff which can be moved to different class. For example, there is no point to like introduce D-latches right away because students will do all designs using flip-flops, and latches become relevant only when you are going to like a low power design with a mid-range clock gating, which is like after you practice already with a regular single clock flip-flop based design, and or latches can be used in things like time borrowing or like latch arrays, which are all advanced techniques, and like latch array can save a few percent of power in certain designs, but there is no point to put this on student right away because he will get confused. Plus, traditional classes have things like Carnot maps, which are also irrelevant because even back in 1960s, there were better algorithms like McCluskey algorithm, and all logic optimization was completely automated when like espresso algorithm came in like 1980s. So now we certainly need to teach students how to develop intuition about critical paths or like logic complexity, but like a Carnot map is just something which like occupies but the Carnot maps just like occupy time in the class, and students don't have time to learn more about like pipelines or flow control or use of FIFOs with pipelines and so on. So one of things is try to and at the same time learning this stuff for too boring. So if a hobbyist take one of like traditional class which do for half a semester and ends with like finite state machine, with like traffic light finite state machine, and uses expensive board, is just not very interesting. So we are trying to immediately introduce graphics and processing of sound, so they can immediately, like once they learn combinational logic, they can immediately draw something on the screen. And when they learn sequential logic, they can do like sound recognition and things of this nature. So this is one of difference in in this related to this textbook. In this textbook, I plan to cross-reference examples we are doing as part of FPGA exercises. Plus, in FPGA exercise lab manual, I want to reference this book. So, and if we look to like some examples, if you look to some examples, like they're like already on a GitHub. So if you go to Verilog Meetup section, go to a repository which is basics graphics music. Hey, yeah. So this is Dan. He is ASIC engineer in Tesla. Yeah. So this has some subsections like labs and hackathon and book, and generally all examples here, they like starting from first design. This is a directory where you have some scripts, some like push button script, and you just tell what board you have, and this push button script figures out what how to create project and script for this specific vendor or for this specific board. So we have like board support packages for many boards, so like Altera boards and Xilinx boards, Lattice, Govin, and so on. But for many like seminars which we do in different places, we are using setup which look like that. So before like Trump's tariffs, this board together with like LCD screen cost just $25. So now after Trump's tariffs, this cost like $42. So even if you apply like 50% markup, which you do on like soldered board, this is still like $60, which is better than standard for many labs like Nexus A7, Arctix 7 board, which costs $350. But the most important thing is this runs very fast synthesis. So especially on Apple Macintosh, this is the only vendor which has a FPGA toolchain on Apple Macintosh. Like on Apple Macintosh, you have like also open source toolchain, which is like USS based. But from proprietary software, Govin is the only vendor which runs, and on Apple Macintosh synthesis rather very fast. While on Xilinx, you wait for like minutes to run like even yeah. So we are using this kind of simple boards for most of introductory classes. But this board can be also used for simple like CPU on level of like ARM Cortex M0, so something very basic. But with slightly larger boards, you can run more interesting CPU. And then if you use high-end Govin board, which costs like $80 or $120, you can actually run a CPU which has caches and MMU, and example of like I will show you later on example of such CPU. And one of things what is actually pending in these activities is to illustrate some something from like more advanced CPU, like branch predictor or like different caches and so on. So we have such exercises, but they're very simple. So and there is like open hardware David Harris and Sarah Harris in Southern California in Harvey Mudd College. So they put detailed description of design of a simple CPU, but this CPU still has like static pipeline, and we don't have good illustration for like out of order or superscalar or multi-threaded examples.
Michigan has an
Huh?
Michigan has an open source SPI CPU with a 5-stage pipeline.
Yeah, there are like maybe more than 100 of RISC-V CPU with 5-stage pipeline, but this is simply not. But students also need to be exposed to like other things, you see, and we will talk about this later. Let me actually present first what we have. Wait, can you hear this? One moment. Checking. No, because I don't hear anything. Just a moment. This actually doesn't have audio. Okay, detection. Okay, this is fine. So you can hear it. Okay, so but before we go, yeah. So when you run example, so let me just demonstrate you the. Oh wait, the USB port. So one thing immediately interesting for the students, and also to like allow some introductory hackathons, which we were doing recently in like several countries. So in Mexico, in Armenia, before this, in like Central Asia, in like Kyrgyzstan, and like other places, and we planned some more such like hackathons. So in order to like illustrate combinational logic, first we do like exercise with like buttons and LED, and then immediately exercise with simple static graphics on this LCD display. And this is how this exercise look like. So a user has a parameterized laptop module. So module which has like parameters of like how many keys and switches it has, and what is the size of what is the width and height of a screen. And in the wrapper, this can be connected to LCD or to HDMI or to VGA or even to like LED matrix. And then we propagate such signals to the user module. So those parameters are like overwritten in the wrapper. Then we propagate to user module. And then in the user module, for example, in this user module, we instantiate module like static graphics, which LCD controller just gives us X and Y, so coordinates on the screen, and we need to create a color. So basically we can train students with a combinational logic just by asking them to draw things on the screen. So just to have like always comp, and then putting if X is more than 100 and X is less than 300, and Y is more than 50, less than when we have usually such like classes are done in together with VS Code. So in VS Code we run this push button. This CPU class. 1 second. So if you go like at this example, so what we do is we just ask students to run VS Code. Cancel. Let's see. So we just ask students to run VS Code. Then we ask students to open an integrated terminal, and this works on the Linux, Windows, and macOS. And then we just ask them to choose a FPGA board. So we run script, choose a FPGA board. So you have to do this only once, and it gives you a list of FPGA boards and of configurations. And then we choose, for instance, this particular board is 10 Nano 9K LCD 480 to 72 TM1638. So this is board number 65. So we just like enter 65, and then we just run a script, synthesize for FPGA. And this just decides that for this board we need to run a Go synthesis. So it runs Go synthesis and places a drought and generates a bit stream and put it on the screen. So now like if you do like 2-day introduction in Verilog, now the question is that how to like introduce to sequential logic in the fastest way. And one way to do this is to simply using artificially slow clock with a 1 Hertz frequency. And then, actually, let's see if I have it here. On screen. Yeah. And then once we like introduce counter and explain how like a counter works, like as a combination of cloud and registers, we just show how you can use a counter bit as an enable. So first we use like artificially slow clock, then we use a counter and use a bit of this counter as enable, like of another counter. So we generally put the enable when counter overflows and has 0. And by doing this, we generate pulse like 30 times a second. And in this pulse, we just introduce offset, and we add this offset to the rectangle. So we have like moving rectangle on the screen. Okay, so now, and once they have moving rectangle on the screen, and we show here like always a block and so on. So once you have moving a rectangle on the screen, you can practice in a Verilog syntax by creating some moving pictures. You see, so this we create like such pictures. Then I ask questions like how do you draw a circle? And usually at this moment, like some students, especially with primarily software backgrounds, they try to like invent a frame buffer or so, but you don't really need a frame buffer for this, because you can just you have coordinates. You can immediately decide whether the pixel is within or like outside of a circle. And then we show them that once they have some moving figures on the screen, they can actually make graphical games, like after 2-day introduction in a Verilog. And then I go with them through a game example. Logic. also, also I run here vendor-specific GUI and show them how schematics look like. And then once they learn concept of sequential logic, I also show them where to get static timing analysis report. So they get quickly introduced to basic concepts. So Verilog syntax, concept of sequential logic, and like a static timing analysis and there, and now they can play with such things and do some like game. So this is a game, and we did some like hackathon. So one object is hitting another object with the keys, and then so like after 2-day introduction to Verilog, they can actually do such like interactive game, and we also introduce finite state machine for this. So this is like a basic introduction. Now, if you want to see. So if you want to run GUI, we can run GUI and we can show schematic viewer. And schematic viewer in Govin is not the best. I think the best is still like Quartus in Altera, but also Xilinx is also fine. But you can see schematics, and we can show for some like trivial examples that so here we can see some comparators and some different flows, and you can show for trivial examples what your RTL constructs become. Yeah, so this is a set of such a fast introductory thingy, and for but people who went through this like obviously cannot pass interview in hardware companies, because this is not enough material, because like companies both like Apple, Samsung and others ask pipeline questions during job interview, so we need like examples of the next level. Yeah, but those are sort of introductory examples. And so now let's go back to our document. Let's close this thing.
Why can't they just simulate?
Huh?
Why use FPGA? Why can't they just simulate?
Yeah, we have example for simulation, which is called system Verilog homework. And those examples, they use Icarus to check functional correctness and use like test benches, self-checking test benches, and have like example with FIFOs and with pipelines. But there are two problems, like three problems actually. Problem one: students don't get much excitement from simulation. So they are more motivated when this is done on the board. Because in simulation, they also need to learn extra syntax about verification. So this like generally doesn't really excite, because this just look like yet another interpreted language with a like programming language with a weird semantics. Second, which is much more important problem, if they do simulation in like in a simulator, they don't get exposed to static timing analysis. So if they put bunch of logic and create like critical path, because in FPGA we have a certain clock, like 50 megahertz clock or 27, they will get artifacts on the screen right away. So like I can actually demonstrate this with them, that if you put like too much complicated stuff, you get a weird picture here.
There are synthesizers online.
There
are open source synthesizers.
Yeah, there are open source synthesizer, and we actually support it. But the problem with the open source, there are two problems with the open source synthesis tool. First of all, like the language support they have, okay. So this kind of not a problem. They do not support some case of like generate or some things in system Verilog latest, but this is fine. You can work around it. The problem is they constantly update the version, and when you get a new update, you may get a bug which students have no clue how to fix. Some random bug in a place and route. And basically, people who write this, like Yosys-based synthesis tools, they just say, "Oh, you need to use different version of Python," you know. And this actually demotivates people generally. So for this reason, so this is like one reason. Second reason, because such examples have to serve students and professors who already get accustomed to some proprietary tools like Xilinx and Altera tools. We need to support them. And if you just tell them, oh, like just abandon and switch, most of them are not likely to switch. Yeah, so this is a second thing. Yeah, but like generally we have it as an option. Just you see, if you go to this very same example, so let's get this example and let's switch to like open source tool for the very same board. So if you go to, let's say, previous example, so what we do is we put 06. Wait, I have it. No, I don't have it here. Let's go to previous example. So here you can choose another FPGA board and you can choose 10 Nano LCD Yosys, so number 64. Or no, this one 67. Let's get 67. So you see, you get number 67, and then you run synthesis, and it runs like open source Yosys tool. But on my computer, with the version I installed, it finally goes to place and route error. So because I didn't update it for a new version, but if I like update it, like upgrade it to a new version, it will run just fine. You see, so see here is that next PNR him. Yeah, so this was some like temporary hack put for this version problem. So they are kind of more fragile, you see. But we do support them. Just I personally mostly using proprietary tools. But we also like another claim to fame is that we allow we have compatibility between with our environment with a tiny tape-out infrastructure which uses open road. So basically we have a repository which is called like which is a template where you just insert top module from FPGA examples into the basic infrastructure. Then you can see this open road with Skywater 130 nanometer ASIC library. You can see all like static timing analysis report. So this is like people who are trained with this, they can use later on Synopsys or Cadence, like Genus and Novus, because they have like things which is different, but still you see static timing analysis they do train students in this way. Yeah, and this open road is supported by UC San Diego. So some schools use Synopsys and Cadence licenses, and some tools recently started to use this like open source base. Yeah, so if you look to this template, this like template has set for tiny tape out. But in source, we created a wrapper layer between project of tiny tape out and the hackathon top, which implements some glue logic, which allow to convert our FPGA design into design for this ASIC infrastructure. Huh?
You taped out an ASIC.
Yeah. So I already taped out 3 designs with this thing. So we can easily do this thing. Yeah. Now if you go back to our so we so far went only through point 1 and we have 16 items. Okay, so next thing is that we also write FPGA lab manual for high school students. So there is a person, his name is Jim Barnham, and he was coming here for last like 1.5 years, so since like January of last year. So and Jim, he worked for 25 years in Xilinx, and after he worked in Xilinx, he he like decided to he decided to become a school teacher, and he is doing like mechatronic classes with like microcontrollers and so on. So he was supposed to write during now sort of like put on hold according to his schedule. And kind of idea is to use a simplified example. So by simplified example, I mean example which do not have a parameterization. Because for the students, it's okay to put everywhere like parameter, wrappers, all this infrastructure. But when you see some like high schoolers, when they see in their module something like parameter and then like WLED -1, this and especially if this is present during the 2-day introduction, this actually confuse people. So for this reason, in our like simplified examples for school children, we use fixed board and the hackathon top with a magic number, so like 70 with a magic number. Yeah. So now this like activity, we put some text together, but we didn't move far, so this activity is sort of like on hold. Then there is a student from UC San Jose who from San Jose State, and just a second, he sometimes join online, so let me just check. Oh, excellent! So we just talked about him. Yeah. So yeah, so he just joined. Yeah. So now so there is student Shiva Swarup, and we discussed with him that you see many schools don't have good verification classes, and they know this because even like 5 years ago I had some like intern like even from Stanford, and I had to actually teach him how to do self put like verification, but when they introduce test benches, they derive it, many of them derive it from a Mentor Graphics Verification Academy, which uses like UVM example for APB, where you are using non-pipeline bus. So you are getting like loop, which is get transaction, put sync on address bus, then wait for clock cycle, put data on data bus, then wait for clock cycle, get a response. But when I had such students on interview like 5 years ago, and I was asking that, okay, you learned how to do this, so now show me how you do pipelined IXI bus, where you can put 3 address back to back and then 3 data back to back, or you can put a read without of order. So you put read request, then with a tag, and then when it goes back to you, you need to reorder back, and you need to have monitor which tracks transactions with the different tags. And when I actually complained about this to Mentor Graphics people, they created like long time ago. They created example for like XI Light bus, which has in the same clock cycle address of next transaction data from previous transaction. But the problem is that they put too much complicated code for it. They put like some semaphores to share bus between threads, and we like perfectly know that all you have to do is that you just need to maintain like current and previous register, and just write like very simple code to support it. So for this reason, I created some time ago illustration how to write this type of verification IP, but my illustration was not using like a UVM. And now this student Shiva Swarup, so they have in San Jose State, they have classes in system Verilog, so they know this like a class higher, like how to put the classes for like driver and for scoreboard, and how to do sequences like UVM sequences, but still they were using examples with the sequential buses, with like I2C or with like APB. So here is a like activity where we want to create a something which is a combination of what they have in UVM with this pipeline, the out of order example, which I created some time ago to illustrate this this concept. So it's in here is a non-UVM XI Lite verification AP, and in this verification AP, what actually I'm doing when I have like, let's get like a maximum example, like pipeline. So when we have a master, I simply maintain a bunch of system Verilog queues and just store outstanding requests in such queues and pending responses in tagged array with the queues. And this allows to both send transaction, have a reference slave, and do monitor as well. Yeah. So yeah, by the way, probably similar test bench can be used for a fetch unit, because I did a similar thing for bus unit in the MIPS course, which like was between fetch unit and LSU unit. So this all comes together, and yeah, you can use like UVM for it, but in UVM there are many kind of, there are problems when you need to create a sequence of something which Yes, so basically there are many companies who are claiming that we're using UVM, but when you actually look to the code, you see that they create some proprietary ways of doing this. Yeah, but we need to have a UVM example, and for such thing we can create it. It will just have some limited ability to put interesting test scenarios. Specifically for like a fetch or for like load store unit. So yeah, this like very interesting project, and like this is not something which have to be done fast, but like as long as it's finished eventually, this can be useful IP for like different students. So now let's go to the next one. Yeah, so another thing, there is a person, Stanley, who came here from of Cal Poly in San Luis Obispo, and we talked with him about micro architectural examples. And I will show you what I'm talking about. And he said that, and this is a common response from people in different schools, that students frequently do not know how to solve them. And I will show you like, what I'm talking about. And those examples also not very solvable by like AI. So and recently some people from like AI companies started to ask me for good examples. So I created an example which current AI doesn't solve well. And coincidentally, the very same examples can be used to like interview students, because solving them shows that students understand how transaction goes through the pipeline, stored in queues, some flow control. A couple of years ago. So, to demonstrate you what I'm talking about, I have a presentation which I did in Armenia, because in Armenia they have a division of synopsis and mental graphics. So uh, they created like some event which was based in Armenia, but with like US companies and Chinese companies and some people who did like papers from Russia. So this is very rare event where in one place you can like assemble all those people. And there, like I went there last March, and I did this presentation about. Just a moment, let me find this presentation. So it's an bit. Yeah, the presentation is called Workforce Development. Yeah, so let me share my screen again. All right. All right. Yeah, so basically here I was just saying that, discussing about EDE industry and stuff. Yeah, and there are some gap between academic knowledge and gap in both like RTL, DV, and physical design. And yeah, so here, like I was showing, this is something which I run through like many students, like tens of students, like equivalent. So something very like trivial for like working RTL designer, but like apparently many students got stuck with. So like I'm just saying that you have like some fixed latency done it properly. So then I check them how to do something with dependencies. And at this moment, many students were struggling. And I can actually check time between how long does it take them. There are some students who like get it right away, but like other students were thinking from like 10 minutes to like 1.5 hours. So basically, some of them start to draw something like this. So block which is square root, then you add b, then you do like another square root, and basically this is like obviously doesn't work because by the time square root of c is calculated, this b1 is gone. So you need to just align the pipeline, and they don't know how to do this. And then they start to like do things like I will store B in a register. And basically I'm telling them immediately this register gets overwritten. Then some of them were asking, can we do square root as a combination module? No, for a obvious reason. Then can I use FSM? And this will kill bandwidth, you know. And one student asked can I use of Tomasulo algorithm because because they were studying Tomasulo algorithm in school, but in a way similar to like uh, popular science. It's kind of stories about like black holes from like Stephen Hawking that many people read his book but don't understand underlying mathematics. So there are students who sort of read it but cannot implement it. But using Tomasulo algorithm for like every single dependency in the design is like nonsense. It's like if you need to dig tiny hole in the garden, you use shovel and you don't call like excavator. So then I was asking whether they learn like shift registers or FIFO or circular buffer. Say, oh yeah, we did learn it in like second month of introductory class. So they learned it, but they simply many didn't know how to use it. And yeah, so this was like first question. Then they, oh yeah, we can actually put FIFO here and put into FIFO when we put into pipeline and pop from FIFO once we get from this like pipeline. So, or you can use a shift register. Then I was asking them, what is the advantage of FIFO versus shift register? And they didn't know implication on power, many. In fact, I at once I met student who spent internship in top company for 6 months or for like several months. I'm not sure whether it was 6 or less on like power. So I asked him how to make a white shift register low power, and he had no clue and started to write something. And what I found is in that company they simply put him to write Python scripts to extract power metrics from output of like Synopsys PTPX or like Power Artist or something. So he never was actually exposed to learning low power problems. Yeah, this like kind of stuff. So yeah, and teachers are saying that we don't have time for this, but they put some like unnecessary materials in so we can change. Yeah, so and basically we talked with person from Kalpoli Pomona about specifically like about specifically making some like event in their place. So we go there, we do event with these FPGA boards, and then we discuss microarchitectural examples. And one good thing is that such microarchitecture which is called System Verilog Microarchitecture Challenge for AI number 2. There was before AI number 1, but no AI could solve it in January, but now AI could solve AI challenge number 1, but it doesn't solve number 2. So what this like challenge is that we use pieces of a real FPU from open source RISC-V CPU, which is called Wally. So if you go to GitHub Wally CPU, so you can see this open core. So this is a CPU which has a like 5-stage pipeline, but in addition to this pipeline, it also has FPU, it has interrupt controller, it has MMU and caches, so it is capable to run Linux. And they are publishing now a textbook which is called RISC-V system on chip design. Initially, they wanted to release it in last New Year, but they're like delaying it. So now it's scheduled to release on November 14. But here they actually put in details all the details of not only details of architecture and RTL, but they describe also like verification scripts around it, verification about like golden model. Against like instruction-based simulator, so they just have quick like Imperas or something mother from Imperas and just compare architecture state in right back or like other similar stages. There are companies like Intel which also maintain cycle accurate simulator, which is probably overkill for most of purpose. But here they put it comparison against instruction-based simulator, and so they put essentially industry-like process in this book. Yeah, and I have text of this book, but I cannot share it because like author shared it for me to review. So this is like a lot of pages, and they go through all the details about FPU, MMU, caches, and so on. So this is like next stage after this basic like Patterson-Hennessy material. So now, yeah, so but let's go back to our list. So next thing is we had event in Mexico just recently, just like a couple of weeks ago, and Jorge, who is usually coming here, but now he's in Mexico. So what they did is that there is some Japanese startup incubator or some like research institute called Mirai, and they assembled Mexican students from like many universities and put them in the same place, and near Mexico City. And we had this event with such FPGA boards and with I mean like interactive event, and then with like open source ASIC. So if you click to this link, you can actually see this event on like LinkedIn and in a Facebook, so we can see it on LinkedIn. And using open road ASIC. So and they in Mexico they created some person is using shutter service, and I think it's not a tiny tape out, but his own kind of clone of tiny tape out. So a bunch of students create their designs and put together in a chip, and then create chip for like many participants who just do their own module. Uh, yeah, this is like a little bit tricky because, uh, but like everybody uses the same clock, and maybe they have some PLLs, but they put hard and put the soul together. So yeah, so uh, next thing what we need to do is that we need to prepare for Maker Fair event in Vallejo. So this is similar to like open source event we had last month, and this is just a like bunch of people who are curious about some like mostly hobby things, like some like Arduino, Raspberry Pi, some toys, some things from like Burning Man. But surprisingly, on open source event, our booth was approached by people from a Qualcomm, from a different UCs, so UC Santa Cruz, San Diego, UCLA, UC Davis, from MIT, from Stanford, and from people from Qualcomm, NVIDIA, and so on. So people do go to such things for like entertainment, and when they go, we can like show some of them this like open source project, and if they want to take part in adding some examples. Contribution to this. So yeah, next thing. So next thing is yeah. So there are some activities which actually have to be done fast. And today I brought a bunch of boards that have to be soldered. So I also brought a couple of soldering irons. So after this, we probably work together with RAM to solder them. So if anybody wants to help, then you can help it too. We need to solder and test and pack many such kits together. Yeah. So if you solder well, you can solder boards. If you don't solder well, you can solder microphones because they're less finicky. Yeah. Then, as I said, that you support many boards. So but there are boards which are not supported. One is a chip inventor board from a company in Brazil, which made like Govin based board. So this is how they look like. One interesting thing about this company in Brazil, this is Van Brown Lab. So this is essentially similar board, but they added buttons so people don't need to connect with these jumpers. And they use this board. They created web-based environment where students put blocks with a mouse and connect things. I personally am not and once industry switched to like HDL is not the is simply a labor intensive way of doing things, but we all draw micro architecture diagrams. So sometimes it's useful to do. I prefer people to just draw microarchitecture diagrams separately and write HDL code. But they are saying that students, and this is opinion, what I heard also from Robert Owen, manager of educational programs of Imagination, that like students like to build systems with a mouse and generate Verilog code from it. So they in their environment allowed to do such things, to create some structure with online editor, graphical editor, and then fill it with Verilog or share it with like AI, and then use some software to put bitstream to the board. So their environment is called Chip Inventor cloud-based EDA platform, and they actually integrated together with ASIC design tools. So you can try something on FPG and then use ASIC design tools. So I discussed this with them during design automation conference, and like I think that their environment can be extended with more microarchitecture exercises and some verification exercises, because this is something what they don't have much. But you see, but they have some also like analog components, tutorials, and they cooperate with actually Malaysian company which is doing training. So in Malaysia, they made government initiative to train 10,000 engineers, both inside and outside and they need some basic idea of how this all works. And then I talked with these people from Brasilia who doing this environment for people in Malaysia, and they said, "Oh, we worked with this Malaysia, so I put just 2 and 2, so it's possible that people in Uzbekistan are using this environment as their training vehicle." Yeah, so we are trying to be. So one project is to be compatible with them, and in order to be compatible, one of steps is to make their chip inventor board compatible with our examples. And this is some activity which is given by which we gave to Asher Robel, but he is cannot come here on every Sunday because he lives like far away and it's like too much driving. He comes from time to time. Yeah, but so like I gave him that board and also 3 other boards, one like small Altera board and 2 Xilinx board to create board support packages for such things. So in order to create a board support package, what you have to do is you have to create a directory in a boards directory. And for instance, if you're doing, let's say, like Xilinx, you need to create a tickle script for Xilinx Vivado, and then create a XDC file with a pin assignment, and then create a board specific top, which is a Verilog file where you connect pins which are mentioned in vendor specific XDC file, and map these pins, just instantiate this board independent module, and instantiate like this user module, which is either laptop or hackathon top, and connect everything together. And sometimes you need to solve problems with like PLL and multiple clocks, if you have like HDMI, or if you have like some other protocols. And like with each vendor, you need to solve different problems, and then you need to modify a bunch of bash scripts we have in a directory of scripts. So here we have bash scripts and like steps, which based on board number figure out how to build a project, how to synthesize, and they're trying to find where the tool is installed by default. And if it cannot find, you can specify it in environment variable, but because most of people install in default location, it usually finds it. For specifically Mac OS, it also has, for Govin, it has to mark their executable like as not a malware, because it's putting of that one a flag. What is the name of this attribute? Or maybe it doesn't do it in like latest version, but it did in like early versions. So setup Govin source. Yeah, so here bash scripts just like those scripts do not run like anything in like a root mode, or no like sudo, but it just means that if you want to do something, you need to do sudo, and you need Linux and so on. So where is the workaround for macOS? Let's see. Yeah, okay, you go in, install Pioneer, macros. Yeah, so you need to remove macOS quarantine attributes, and by doing this, it's saying that you need to do xatter-rd to remove quarantine attribute. Yeah. So to add some new board, and especially new tool chain, you need to essentially modify board specific files, and you need to modify such scripts. Yeah. So next thing, we also need to create board support packages for Govin boards called Kiwi from Vietnam. This is some new set of boards, and this is remarkable because Govin Semiconductor, they put those boards to their their page, so it will get more exposure for like in the US market, because this thing now you need to like order from China using AliExpress. So recently their price increased twice because of Trump's not twice, less than twice. It was like this basic board was like $13 plus delivery, so total of 16. So now it's like $25 plus delivery, so 30 something. You know, yeah, like twice. So this Kiwi board is something similar, but with a similar price, but it's simply not supported. It has this Kiwi 4K board with a camera, and like Dan, he is now working on example for camera, which we need to put as a demo. Yeah. Now, so this activity is not allocated to like anybody yet. So if Matthews Stankas can do this actually would be a great idea, because this is something which actually does have priority. Yeah, let me ask second. Yes, XDC file. Yes, so this is question about what is XDC file used the same as XDC. Okay. So there is a question from Nick about XDC file. So let me answer this question. So Xilinx has a proprietary format called XDC. In practice, this is like a TK format, but like in disguise, sort of. So let me share the screen. So GitHub. So let's quickly see difference between this formats. So if you go to boards, and if you go to, let's say, basis 3, you can see two files. One is XDC, and in XDC you also specify pin connection. So you're saying that the pin number V17 and Xilinx synthesis tool knows what this pin means, is connected to our named port SW. So it establishes connection between pins from the datasheet and the names of our port in Verilog module. In addition to it, XDC file also do something like create clock. This is actually TCL file in a TCL language, but they extended TCL with these commands like set property. If you look to like other boards, if you look for example, Altera board, let's get this board 10, which is Altera board. They have file with format QSF, which is also TCL in disguise, but they use different commands like set location assignment that pin M15 is connected to port key 2. So now if you look to our Verilog file, in a Verilog file, wait, it's the same as Xilinx. So in a Verilog file, if you go to, some of these board packages, they just cross-reference each other. So if you go to Xilinx, you can see that, let's say M15 is a key 2. So if you go to the board, you can see there is the input key 2. And this key 2 is mapped to a signal called key. And this signal key is passed into a laptop module. So here is key.
These two files, they automatically detect each other, or we have
script knows. In a script, synthesize creates a project file where it specifies QSF file, and this QSF file defines Verilog files here. So they're not defined here, but let me actually demonstrate how this works. So if you go to Visual Studio, and if you get, for example, lab, if you get, for example, lab basics counter example, like a binary counter. So let's create. Let's open an integrated terminal. So suppose we choose 06, choose another FPGA board. Suppose we choose board called Xilinx, which is board number 47, right? So we run the very same script 03. But now here script on the fly creates Yeah, so now it's running static timing analysis, but there is no board here, so like it failed. So now if you go to run directory, you can see that it created a file called FPGA project QSF, which is a combination of QSF file from our board support package together with all Verilog files it uses. And you can see that it's specified here board specific top SV. And this board specific top SV is a file from our board directory. So it combines, so this QSF file refers to system Verilog file. But this is how it is done in Altera. In Xilinx with XDC, it's done in different way. In Xilinx, if you change the board, let's say that you put board 0, wait, so 06, choose another FPGA board. Suppose you get board like basis 3. This is board which many schools use. So if you run same synthesis script, it will create different run directory. It will run actually for a long time because Xilinx runs for a long time. But it will create TCL scripts, configure and synthesize, which we get from another directory, and then it will run such script. So this synthesized TCL refer to XDC file somewhere. And so XDC file is same as QSF, but with vendor specific commands, and it's only about pins. So in addition to XDC and QSF files, there is also SDC. If you go back to our directory to boards, to Xilinx, let's go back to Xilinx. You can see that Quartus also requires file called board specific SDC, where it does create clock. So you see this clock, create clock command is very similar in both like ASIC design and like Synopsys VCS in like DC shell. You also put like create clock, and similar to Vivado, Xilinx, and similar to Quartus. And if we are talking about Govin, so Govin also has let's get our board like 10 5K board. So, but Govin has, instead of XDC and QSF board, Govin has board specific CST, where you just define pin, logic pin name in your module, and pin on your FPGA known from the datasheet. So this is same thing, but same thing with different syntax. And that's why we don't want to expose user to it. Because after graduate, like after student graduate, who knows what he's going to use? He can use like Xilinx, Altera, Lattice, Govin. He can be ASIC designer, whatever. So, but vendors want students and professors to get stuck to certain toolchain. So for this reason, like Altera and Xilinx, they show tutorial. Send it to professor. This is like good for you. Get this GUI and with mouse draw the chips, and then go to like another GUI with a spreadsheet and put some like attributes of those pins. So from my perspective, this is not efficient way of spending student time, because we all want students to learn micro architectural tasks rather than to do something which like anybody can do, like a mechanical thing, like going through the spreadsheet. So here we like isolated in such like a QSF and other files. scripts, we like isolate user from such files. Also, Lattice has similar type of file. Where is the Lattice? Yeah. So if you go to, let's say, like Lattice open source boards, you can find something else. Okay, but back to our list. Yeah, okay. So question to Matthew. So can you hear? Yes, Matthew, you're on mute. So do you think that you can help with support for this Kiwi board? Because if we do support for Kiwi board, we can just get some benefits from Govin marketing. They can at least publish some posts on LinkedIn about us and so on.
I mean, something that I can absolutely try, but
yeah. So this Kiwi board, it is available in a principle. We can ask Govin marketing to send it to you, but this kind of hassle. This is cheap board. So what I think it's now sold on Amazon. So let's see, Kiwi FPGA board. And this is a good practice in using this board support infrastructure. Okay, Kiwi. Oh, yeah, Kiwi $14, free delivery Friday. You see, so you can get this board, and but this board has very small FPGA, which has like only like 1,000 something lots. So you cannot run all the examples on this board, but you can connect the TM 1638, and then you can connect it to VGA adapter, or we can use some adapter I ordered. Let me find this. Like I ordered a bunch of VGA connectors to GPIO. Let me find, it's in something as star. Yeah, it's called, no, it's not it, tiny TPU. Tiny tape out VGA. Let's see. Hello LCD. Tiny tape out. Yeah, tiny tape out VGA. So there is a tiny tape out VGA. Yeah, it's called tiny VGA P mod. Tiny VGA P mod. Tiny tape out. No, this is something. This VGA. Yeah, this one. There is a tiny VGA P mod. It's something which can be ordered directly on a factory in China. And I ordered like I think easy 50 or 100 of them. So this has only 10 pins, and we can connect those pins to this Kiwi board and just have some graphics based on such simple board. So basically, what I want you to try, I want you to try to like order this board and then use the 10 Nano 9K as an example to connect tiny VGA and to connect TM1638 connector. So this is the very connector we use, and then see what examples are going to fit in this board and what are not going to fit. So this uses TM1638 connector you have, and you need to like analyze which GPIO pins are suitable for use with this board. Need a setup which runs at least some examples. So this is mostly just like common sense to like analyze whether example is fit and what what pins to connect and so on. And if you think that this board is not good for our purpose, then Kiwi has other boards which, for example, use Kiwi 4K Govian, which uses Kiwi 4K FPGA board, which has a connection with a camera. So this is similar to Tang Nano 4K board, but is slightly different design, or maybe even design is the same, but I didn't analyze it yet. This has also HDMI interface to graphics, so you can try this board, but first probably you need to compare it to Tang Nano 4K. Maybe this is kind of the same design, and if it's not the same, then we need to figure out what is the difference. So this Tang Nano 4K board is already supported by our examples, but we don't have a camera example for it. So here we will talk about what Dan is doing right now. So let's go back to our document.
Can you share
Yeah,
the link
so
of where
next-
to buy the VGA adapter?
Huh?
Can you share the link of where to buy the VGA adapter?
Should I link what? Oh, I didn't hear you. You well. Can you
Yuri
repeat?
is asking for VGA adapter, like the visual graphics.
Yeah, this VGA. Yeah, you want me to share link
Video
with you? Yeah,
graphics.
yeah. Let me share a link, and maybe I will put link to this document. Yeah, so this is called tiny tape out. Tiny tape out VGA. Yeah, it's called Tiny VGA P mod. Yeah, it's called Tiny VGA P mod. So let's put it here. So here it is sold for 15 euro, but actually I ordered it for amount much less because I ordered it in bulk and I put order for the board. So I have like a bag of like 100 of them, or maybe yeah. So you can add. Oh, sorry. So you can add. They can be used with this tiny VGA P mod, and this tiny VGA P mod is called tiny VGA. So let me add this to watch. Oh, but I already watched it. Yeah, let me put it to start. Yeah, so if you go to this website, it actually tells you how to order it in JLC PCB. And I did order it, and it's very easy. It's like how you can order your own PCB board. It's like very cool. So they have some website where you just put design files. And if you know how to design the PCBs, you can put your own design file and you can put assembly instructions. But if you don't know how to do PCB and you have some friend who know how to do PCB, then you can ask friend or hire somebody if you have extra money for it and to create such design. Yeah, usually PCB design are not like as expensive as the ASIC design. So, so we are not like talking about like $1 $1 million kind of project, but more of like several $1,000 kind of project. So yeah, but let's put so let's actually put it here. Yeah. So yeah. So like Matt, so you can just investigate it. This is kind of kind of exercise where you understand the whole infrastructure better, and it's mostly nothing difficult from microarchitecture standpoint. It's just a common sense applied to like various components. So you need to see how tool chain is working, so troubleshoot things and so on. Yeah. Also, if you already have Orange Pi MSOC board, like MSOC, you can check the design which was implemented by Vadim Ostrikov. But the problem is, so he implemented, but he put some strange connector which I don't have. So somebody needs to investigate a type of connector he put. Yeah, I will just shoot email to Vadim, I think, because he added this board and he added some picture how to assemble it. So let's see. So he put some example into Melody, yeah, answer, yeah, waveform generator. I think he put it here. Waveform generator, oscilloscope. Yeah, are you asking? Or maybe this is in the documentation. Yeah, but it is necessary to like verify what he did actually. Yeah, I will talk to him. So next thing is that for a long time I wanted to find owner for the lattice board support, because I have like 7 lattice boards, and we do have support for some of those boards, but this support was initially made by a person, Ruslan Galatov. So he actually lives in a Tyumen, in a city in central Siberia, where you get minus 50 degree at winter. So really cold place. And he is making contacts for like United Arab Emirates industrial automation. So he created his own lattice boards, and he put example. And also by doing this, he also put examples for like other lattice board for like orange cardboards. But then we had some disagreement about the code organization, because he is more like software person. So he wants to put all code in one giant, always at a postage clock block. And so I said that the way how he is doing this is like not scalable. This will ensure too many maxes and so on. So then he like lost interest in doing this, but he is okay to like consult somebody how to resolve problems with the lattice and open source tools. So I mean, like, you can call him now, because he like doesn't sleep at 3 a.m. So now in Chimens they have approximately 1 a.m. So he's like available, but he is not like actively adding new boards, because actually he like doesn't need to. He has his own board, plus he has Orange Hub, and he's not interested in adding new boards. But if somebody can investigate and take ownership of this, I will show you how those boards look like. You see, you have a bunch of such like lattice boards, which I bought with the whole. Yeah, this is, for instance, Orange Cub. Oh. So somebody needs to just get the code we have and like independently verify it. Plus, there are some other words. For example, is this one? Yeah, and with lattice, yeah. So here, so lattice like a claim to fame is that they are inexpensive. But they are less used than like Xilinx and Altera. And in terms of Govin, I'm not sure. But if somebody can figure out, yeah, in addition to it, Ruslan is a fan of everything open source, so he didn't put proprietary tools. And he put only USS-based tools. So if somebody can also figure out proprietary tools, this would be a good idea. Yeah. So he is like another step, like step. So we have like this type of board. So let me show this online. Just boards. Let's put stop share. So let me show this to all. To the camera, how this. For example, this is like a small lattice board we have. Then we have orange crab. So then we have orange crab. This is like orange crab board. Yeah, and they also use for some of them use external chips to configure those boards. So it's also necessary to figure out how to use them. This would be really cool. And the significance, another significance of lattice is that lattice boards are used by. So there was a company eFabless which now went out of business, right? eFabless, it's a company which made a deal with Google, and they sponsored doing ASIC design by like academia and practical people using the Skywater Fab. So you can pay like $10,000 and like order ASIC using Shutter service on Skywater Fab. But they went out of business in February, but the founders already created another company called something like let's see. So I was talking with them that we need to combine combine FPGA and like a basic. So eFabless. So eFabless went out of business. So now they created another company. Oh, wait a second. They still have. Due to funding challenges, shut down operations. Okay, so this is called cheap. What is the new name of eFabless? You can find them on LinkedIn. Yeah, so they created new company where just like what I recommend is to use Govin, and then from Govin move to like tiny tape out. But they now want to use lattice based board as their prototyping board. So practically it's a common connection. Yeah. Yeah, so Jeff Di Corpo Mohammed. Yes, okay, so Mohammed. Yeah, this is the guy. Mohammed. Yeah, here. Yeah. So the founder of eFabless, Mohammed Qassem, so he now is doing a new company which is called Human AI Collaborated. What? Chip Foundry IO. Once they're opening and closing companies too fast. So in February it was eFabless, and now it's something else. Okay, Chip Nano Hub. What is that? Okay. So Jeff DeCorp is his. Yeah, it's called a Chip Foundry. Yeah, it's called a Chip Foundry IO. So they have a. Yeah, it's called Chip Foundry IO. So if you go to Chip Foundry IO, they already have MPW shuttle, and they created NVM. Yeah, so you see, they essentially same thing what I discussed since like last year, and even made demo in their booth. So they make some like rapid prototyping, education, and they have a cheap create. So now they charge not $10,000 but $15,000 for the tape out, and they have a cheap Discover platform, which is a FPGA based board, and so they get design from FPGA and put it to their ASIC platform, and or maybe they do it through like tiny tape out, but like tiny tape out was using eFabless before, so they essentially were putting order for 10,000 for eFabless shutter. They split this like 10,000 into many people, like individual students who pay only like $50 per tile. Yeah. So now so if we support lattice, we in principle have better integration with this process, but ultimately it doesn't matter, because just like what they do, they design on lattice and then put tiny tape out. We can design on Govin, Altera, or Xilinx and put it in tiny tape out as well, because we have template for it. Yeah, so this is another activity. Let's see. Yeah. Yes, I put purchase link, so let's put purchase link. So this is tiny VGA. So now, yeah. So now we also can create a demo that integrates Tang Nano board with a Geiger counter of radiation. This is what this Geiger counter from a person on Maker Faire 2 years ago. He is actually working as director in NVIDIA, but just like what we put things on Maker Faire, just he put his booth on Maker Faire and was selling Geiger counters connected to okay, let me find it. Connected to microcontroller. So I created connection to like Altera FPGA board, and I want to make same demo for Govin. So let me find this board. Yeah, so here is here is this gentleman from NVIDIA. This is his board. Yeah, so he created his own company called GG Labs, and when we did this seminar, I don't. Oh yeah, so you can see actually how this looks like. So this is the video. So this is this GG Labs thing connected to Altera FPGA board, and if you actually put uranium salt next to it, it produces more particles, so it shows more particles here. So I just gave this board to Asher Vrobel, and he is looking at it. Yeah, then Dan is working with 10 Nano 4K, so Dan may share his first experience. And one a gentleman, his name is Jasmine. He lives in San Diego. So just like me, so like I came to California back in 1991. So like I'm originally from Ukraine, from Kiev, and then I was educating in Moscow in Russia. And then I came to California in 1991. And he is like same thing. So he was in Yugoslavia when it was still sort of one country, just like I was. And my father is Ukrainian, and my mother is Russian. So for me, this is sort of like Southern California and the Northern California, you know. So now they have this conflict. So I'm waiting until it's sorted out, so I can go to both places. So, but like Jasmine, he was in former Yugoslavia, but then he went to Canada, and now he is a contractor for Verilog in San Diego. So he decided to make a seminar in Bosnia, like invite people from Serbia, Croatia, and Montenegro, and we like discussed this for some time, and we even put dates on it, but then it went into he wanted to have like sponsors for it. So usually I'm making some of my seminars using of my own money, and for like other seminars there are some universities who are willing to pay something. So he wanted to find some commercial company who can sponsor the whole thing, but this is a kind of tall order. So and then he decided to postpone it, but maybe we can still organize it. So there is such activity, and they want Jasmine to come from San Diego here in September and help us in making demo on us over Zoom here in Hacker Dojo. And in Kenya, they this is kind of interesting. They have like several thousand of engineers. They produce like their education system produces like several thousand engineers, but most of them actually do not work in Kenya. Most of them are doing some remote contracts, so like microcontroller programming. There are few engineers who work inside Kenya on things like industrial automation or like vending machines with the microcontrollers. So they are now researching whether it makes sense to extend their curriculum with FPGAs. And they had some experience in the past where some like US companies were like selling them, or like European companies were selling them some like equipment like a 3D printing, which is kind of fun to have, but it doesn't lead to jobs. So now they want to make sure that like if they start to teach people FPGA design, those people will be able to find jobs. So now we are trying to figure out how to present a case for them. And if such case is presented, if they figure out that it makes sense for them to like educate locally FPGA design engineers, then we can fly to Nairobi and make a seminar there. And the cool thing about Nairobi is that they have like giraffes and elephants walking in the city. So they have park in the city, which is not a zoo. This is just park. Like here we have like Rancho San Antonio. They have such park within like city borders. But in Rancho San Antonio, we can see only like coyotes and turkeys. But they have like elephants, giraffes, or like serious animals. You know. So yeah, and this is. So you can see, for example, this is LoRa board for Internet of Things. So LoRa is Internet of Things protocol, and this board is called the VASI actuator. So those are boards designed in Kenya, but they mostly manufacture things in China. Also, they have like 3 PCB PCB boards. So you see VASI Hub Pro. So now it's generally pending on marketing research whether it makes sense to educate engineers, FPGA designers in Kenya. So and the person, people who are sort of driving it, Philip was working there for like 20-something years building mobile networks in Africa. That's why like Kenya has very good high-speed internet. But and their university together with others, they have classes on like STM32. Yeah, then we have also a couple of like online platform for system Verilog homework and formal verification, and this is it. Yeah. So then I put some like recommendation about board support packages and about what to study. So this is like a list of activities. Yeah. I started speech about this and it went for too long. Anyway, now where is Dan? Let's ask Dan to talk what he learned about camera. Okay, is Dan here? All right, so I finished my speech, so now it's your turn to talk what you learned about.
Yeah, so finally got going. Yeah, just set up cameras up.
Mhm.
Let me get a preloaded,
Huh?
preloaded drive, preloaded drive.
Ah, yeah. Mhm.
Can I get a
So,
preload
yeah, but how do you want to use it?
for all the software installed?
Ah, yeah, yeah. I can give you just a moment.
Yeah.
Okay, so now let's discuss. So then just did some experiment with the cameras. So because Dan is actually he is working with cameras in Tesla. So now we want to create sort of like an open source example of something what people can relate to.
Yeah,
Yeah.
so.
Mhm.
it's only like- So one of the labs I'm working on a lab using just a simple little camera with boards. Have some simple tech. Hoping you should have that ready by the body. And software tool on the hardware. So. Yes, can you need help with anything you have questions, just ask, tell me what you've done before, what you're interested in. So, and also, or what I say. Still important. So the what exactly the demo